We're going to spend a little bit of time talking about elastic properties of materials. This sometimes goes elasticity. So we want elastic properties. Thus far, we've talked about two kinds of objects: point particles, objects that are just points, and rigid bodies, objects like this piece of chalk that are rigid. It turns out there is no substance in the universe that's perfectly rigid. Right? Every substance, no matter how hard it is, if you put a large enough force on it, will change. It might change its volume. It might change its shape. Okay? Even something as hard as diamond can be, you can put a large enough force on it to change its shape, for example. All right? So we need a way of measuring or quantifying those changes. All right? So the first way is that if we have an object and we press on it, all right, the object's volume will change. All right? And that's what's called the bulk modulus. So we want to measure the bulk modulus. All right? So the definition is the following. All right, so let's explain what each of these things are. So this is the bulk modulus. This is the force on the surface of the object divided by the area of the object. Right, so imagine you provide a uniform force on the object divided by the area. That will tell you what is called the pressure on the object. Right, this is the pressure. So for example, in a balloon, I can push on the balloon, and I can, if I pushed everywhere, I can make the balloon get smaller. Right? Or if I took a balloon at sea level and took that balloon and with me while I hiked up a mountain up to the, a few thousand meters, what will happen to the balloon? Will its volume increase or decrease? What do you think? It would increase? All right, so the volume of the balloon would increase. Why is that? What? Pressure goes down. All right. Okay, so the pressure has decreased. All right, and so the volume of the material will increase. All right? That's what this minus sign is about. Right? So if you add an external pressure on the object, okay, its volume will decrease. So that means that delta V will be negative. So if P is positive, delta V will be negative. And that cancels this negative, and therefore we get a positive bulk modulus. In physics, we always like properties of things to have positive numbers as much as possible. So we define things that way. So this is a definition of the bulk modulus. So what has the largest bulk modulus? The air in a balloon, the water in a container, or this piece of chalk? What has the largest bulk? So that's right. A is gas. B is a liquid. C is solid. All right, so I want everybody to think about what has the largest bulk modulus. So how do you look at this? You add some force on it, and then the volume changes. All right, so it's delta V. So for a given force on an object, if it's a gas, will delta V get big? Will it be, the change in volume be biggest or smallest? It'll be biggest. So what will happen to the bulk modulus? Smallest. Okay? So the solid has the largest bulk modulus, right? Is that right? Yeah. So the solid has the largest, liquid next, gas the least. Okay? Everybody good on that? All right. We had answers all over the place. Yeah. Okay. All right, so that's the bulk modulus. You can define a bulk modulus for a gas, a liquid, and a solid. All right. Now, the next quantity of interest is called Young's modulus, after somebody named Young. Okay, Young. And the idea here is we have an object, and we exert a force on it, and the object has a cross-sectional area, A. All right? So what will happen to this object? So if I had a rubber band, for instance, and I pulled on it, it gets longer. Okay? So Young's modulus is defined this way. This is the length. All right, so we pull on it, the length of the object will change. Okay? We do not need a minus sign here, right? Because if I pull on it with a force per unit area, then delta L will increase. Okay. This is called the stress on the object. And this is called the strain. So the stress is the cause of a strain. All right? Notice the strain is dimensionless. It has no units because it's a ratio of two quantities with the same unit. Okay? So that's Young's modulus. Do you think a gas or a liquid can have a Young's modulus? Does that make sense? Not really. If I have a gas in a tube and I pull on, I don't even know what it would mean to pull on the gas. I couldn't even do that. All right? But certain, and the same thing for a liquid, couldn't do that. Has to be able to maintain some kind of shape, some kind of rigidity to do that. A rubber band does have a Young's modulus. And that Young's modulus will be very small, because a small relative, any force will lead to a big change in the length. All right? Polymers can have a Young's modulus, at least given that. All right? But mostly Young's modulus is for a solid. And it's pretty small. It's pretty big, rather, because if I give a force on this, delta L is very small, right? I mean, I'm pressing on this chalk pretty big. I'm probably not changing its length hardly at all, right? So Young's modulus is a relatively big quantity for a solid. Okay? And it measures how rigid the body is. All right. Now there's one more elastic property, which is probably the most important one that distinguishes a solid from all other materials. Okay? And that is called the shear modulus. So the basic idea of a shear modulus is you do the following. You exert a force in this direction and an equal and opposite force in that direction, and that will cause this object to do something like this. All right? And we call this distance delta x, and this distance h. And then again, we have an area here on top. So the force per area on the top. So if I have something like this, I imagine I take a force this way, and then an equal and opposite force down here, and that'll cause this thing to change its shape slightly. The amount delta x over there, that's the delta x. H is this, and the area is the area up here. So the shear modulus is defined as F over A divided by delta x over h. Again, this is called the stress, and this is called the strain. Okay. Sometimes people call delta V over V the bulk strain. I haven't really heard that term that much. Usually strain is referred to this way and this way. Now notice what happens here. So I take two surfaces and I'm pulling on the surfaces and changing the shape of the object in doing so. If you have a liquid, there is no shear modulus or fluid. Okay? And even a polymer will typically not work very well. Okay? You have to have a solid to have a shear modulus. Okay? So what distinguishes solids from most other materials, the most important property is a shear modulus. So I do research on melting. I take a crystal and I raise the temperature or I lower the pressure on the material, and eventually the material will melt. I don't actually do this in a lab. I do it on a computer. All right, I have a bunch of particles. They're in a system. They interact with each other. Okay, and at some point, if I raise the temperature or lower the pressure, the thing will melt. How do I know it's melting? Well, there are various measures. I can look at the particles and see where they are. But there are certain quantities, certain situations where you can have the particles can look random, unlike a crystal where they're separated by equal spacings. So in a crystal, you might have particles that look like this. They're very regularly spaced. And they're just oscillating about a lattice site. So that configuration is a crystal. But I could have an amorphous solid where the particles are pretty random. So this would be an amorphous solid, or even a glass. And this is like a crystal. Both of these will have a shear modulus, a non-zero shear modulus. So how do I know in my simulation whether it's gone from a crystal to a liquid? I cannot just look at the particles. One really good measure, in fact, the only thing that is absolutely sure to tell you is that in a liquid, the shear modulus goes to 0. Okay? And one can actually measure that in the computer. There are ways of measuring the shear modulus of your system. So the shear modulus is the most important quantity for distinguishing a solid from a fluid.